Let's start with the easy part, though. I guess the atomic theory part. Let's talk a little bit about atomic theory really quick. So this is in chapter 1 of our textbook, in case you do have your textbook. Chapter 1 and chapter 2, specifically chapter 2, I guess. Yes, chapter 2. Chapter 2 starts the history of the atom. You can go on page 33 of the textbook, and that's where the textbook starts to talk about the history of the atom and what different scientists did to come up with their ideas. Alright, so chapter 2 was the first chapter that starts mentioning what the scientists were doing. So if you read through it, you have the parts that talk about the early history of chemistry. It's going to very quickly go through some of the things that scientists did. I think the main scientists I do want you to focus on, let me write that down for you. The main scientists that I think you should read about very briefly would be John Dalton, of course. Okay. John Dalton and his 4 postulates. I want you to read up on John Dalton, specifically his 4 postulates to atomic theory, those 4 points that he made, because you will have a question on the exam that's asking you about those 4 points. It's going to ask you about whether those 1 or 2 or 3 or 4 of them are still true today in 2016, or if they're not true. If they are true, tell me why we believe they're still true. If they're not true, tell me why. Of course, we know there's at least 1 or 2 of them that are not still true. Please read through your notes on your own to figure that out. You will have a question that's going to ask you about Ernest Rutherford. Does anybody recall the name of the experiment or what he used in his experiment? He performed the gold foil experiment. What did he discover at the end of his experiment? Before we even go into what he did, what did he get out of it?
Something was reflecting back the light or the...
So I guess let's go ahead and talk about that then. So in his experiment, he was shooting something. Do we recall specifically what he was shooting? Because it is crucial to know exactly what he was shooting. Regular chemistry, we don't really emphasize too much what he was shooting and what he was shooting those things at. He was shooting positively charged particles, alpha particles, or what we were calling them. Other people call them, I guess you could say hydrogens. He was shooting positively charged particles at gold atoms. Now, he was not aware of what was inside of the atom, but what he did know is that if he was shooting those positively charged particles toward the atom, if it would hit towards the middle, the particles would be deflected back towards him. As long as he hit towards the middle, they would always deflect backwards. If the bullets were hitting maybe like the top or other areas, they would go through. They would go through. If I'm shooting something positive and every time I hit towards the middle, it's deflected back, what can you conclude from seeing that? What are some things we could think is causing this or explaining what's going on?
The center is positively charged as well.
Before we even talk about it, there's something in the middle.
Okay, that if I'm shooting anywhere else and it's just going straight through, But if I'm shooting towards the middle and it bounces back, that means there is something in the middle of the atom. Now, in 2016, what do we call the center of the atom? The nucleus. So that's the first thing that came out of Ernest Rutherford's experiment, is that there is something in the middle of the atom. We call it the nucleus. The nucleus is not an object, it's just an area, because we do know that there are things in that area, but at his time he did not know that there were actual items, specific items in the middle. He just thought, okay, well then maybe there is this little circle, this little circular area in the middle, and we'll just call it the nucleus. Now, what else can we assume about that nucleus if the positive things I'm shooting at it are being deflected away from it? Say it again.
It has a positive charge.
There must be some type of positively charged force in that middle area. If I'm shooting something positive at it and the positive things won't stick around, what's the only force that will immediately reject something positive? Something else that is positive. Because we know that two positives are not attracted to each other. If you have something positive approaching something else that is positive, they will not stick together. As a matter of fact, if you get close enough, they will approach a distance where they cannot even get close enough. They will have to bounce away, depending on how fast you shoot them, right? Because if I have two magnets and I have the same magnetic sides approaching each other, I can use my hands and force those two magnets to get close together. But you feel like as soon as you get those magnets close, they do what? Like start sliding against each other. If you ever played with magnets, try doing that. Now, what if I have a positive force approaching something? What if I have a positive force approaching something that has neither a positive or a negative charge? Do you think I can get that positive force close to something that has no charge? What happens if you take a magnet and you put a magnet next to something that's not even metal? Nothing happens, right? I can take a magnet right off my wall and stick it to this paper like this. Nothing will happen, right? Because it's no attraction. Will it stick around? Like if I put the magnet on the paper and I release the magnet will just fall, right? We've seen that before. So what would happen if there was nothing charged then? If he was shooting these positively charged particles towards the nucleus, do you think that these positively charged particles will immediately be bounced back? Or what do you hypothesize would happen? Maybe it'll be bounced back but delayed? Possibly. What are you saying, a transfer of some type of charge? That's something I never thought of. I wouldn't know. But what I will tell you is that on the exam, it will propose an actual situation. And then you have to come up with a theory about what you think will happen, or what do you think he would conclude, and you would have to tell me why based off of what you currently know about things. So one question will say, what if the nucleus had no charge at all? What do you think would happen if a positively charged force was being shot at it? Well, I mean, your options are either it'll go through, bounce back just like it already was doing, or some variation in between. You have to come up with your own theory and just make sure you have something logical to say about it. I could have two people give the same answer. One person gets it right because they convinced me enough with what they said. Another person would get it wrong because they did not convince me with what they said. But what if the nucleus had a negative charge? What do you think would happen if something positive was being shot at something that had a negative charge? Then what do you think would happen? It might stick to it, right? Possibly. These are things that you want to think about. So you may have a question, you will have a question asking you something like that. Okay? I think on that exam is only John Dalton and Ernest Rutherford. J.J. Thompson's plum pudding model was too stupid. I'm not putting that on the exam. No offense, J.J. Thompson, sorry. And Niels Bohr is everything in Chapter 7, so you're not going to have a Niels Bohr atomic theory question. It'll be in the Chapter 7 section, okay? Just say theorize, also conclusions, explain the conclusions, agree, disagree. So that's for atomic theory. That should be the easiest part. If you want a refresher on atomic theory, there's a bazillion videos on YouTube. But of course, Chapter 2, reading through all of the first part of Chapter 2, if you want to read through the textbook, it's very short, but that's what I would do. But here's atomic theory for Dalton, 2.3. Here are the 4 points. If you're wondering what I'm talking about when I say those 4 points, that's on page 47, so make sure that you look at that. We're not asking you about the law of multiple proportions. Do not worry about this stuff here. I'm not asking you about any law of conservation of mass. None of that, because we'll have plenty of fun with that when we get to reactions, so don't worry about that. Okay. That takes care of A. B, atomic structure. I'm not going to insult your intelligence. But for the sake of those that had to learn this for the first time, or those of us that had a crappy chemistry teacher, no offense to anybody else who watches this video, anyway, I'll take that out. Because I don't want nobody to say, Ms.Harris was talking about y'all on the video. I'll just take that out the video. But if you never learned how to use the periodic table to do atomic structure, we'll do a very, very quick review. But this should be the easiest part of the exam for us. I have not a single piece of white paper around. I'll use this. Alright. Atomic structure. You only need one thing to answer these questions, and that's your good old periodic table. I will be providing you a periodic table, a blank one, so you will not be using your own. I will be giving you one. The only things I'll be asking you for atomic structure part B is to either tell me the identity of the element, the Z, and what does Z stand for? Atomic number. I may ask you to calculate the A. What does A stand for? Uh-oh, not atomic number. Oh, it's mass number. It is so confusing. I hate that. I wish that we never did that. I wish atomic number was A and mass number was a capital M, or make it Z or something. But this is the way it is. I will ask you to calculate Z, atomic number, A, mass number. What information do we get from the atomic number? Number of protons, and you also get number of electrons, assuming that the atom is, if it is neutral. What does it mean to be neutral? There's several ways to explain being neutral. One way to explain being neutral is that your charge equals 0, meaning you are not positive and you are not negative. You have 0 charge because all of your positives cancel out with all of your negatives. Okay? That's one way to think about it. Now, what do we call an atom that has a charge? We have a specific word we call an atom that has a charge. It's called an ion. If you are an atom that has a positive or negative charge, you are now called an ion. How would I become an ion? Let's look at an example of, let's just talk about hydrogen. The smallest and simplest element on the periodic table. If I am hydrogen, on the periodic table, if it's neutral, what information do I know about hydrogen? Hydrogen has a Z of 1. That means it has 1 proton and it has 1 electron. If I'm telling you that the mass of hydrogen is 1, how many neutrons does it have? 0 neutrons. Because if this is your mass number, how do we know the mass? How do we calculate the mass of a proton? Of an atom. Protons plus your neutrons. If you've never covered this, then you're probably like, what the hell is all of this? But this is fundamental stuff that you've hopefully practiced by doing those quizzes online and the stuff that I've given you. If you practice this, hopefully you know this stuff. If not, you got a lot of work to do tonight. So this is how heavy hydrogen is. You add up the protons and the neutrons to get that. So 1 plus 0 gets you 1, all right? If the Z is 1, that tells you you have 1 proton and you have 1 electron, all right? Now, if you add up your 1 positive and your 1 negative, that cancels out to have a 0 charge. So that means hydrogen is neutral. But if I tell you that now your hydrogen will have 1 proton and 0 electrons, what would the charge be on that hydrogen now if it has 1 proton and no electrons? Somebody took its electron because it was on the outer ring ready to fly away anyway. It will now have a positive 1 charge because you only have 1 positive proton and you have 0 electrons. So you have a positive 1 and a 0, that makes a positive 1 charge overall. So now you have a hydrogen ion, and that's called H plus 1. But we go way more into that with the next stuff that we'll be doing this next 6 weeks anyway. Okay? Will you be asked questions about ions and whatnot on this exam? No, I'm not going to ask you about that because that's going to be the ionic and covalent stuff that we'll be covering very next in the upcoming weeks. But you will be calculating mass number. Okay? So you have atomic number, mass number, counting protons, neutrons, and electrons. Make sure that you know average atomic mass. You'll only be given 1 question on that. I never ask a bunch of questions about that. You'll probably only see 1 on the exam as well, the AP exam. Example. I think 97% of all hydrogens are H1. Then you have 2% of hydrogens are H2. 1% are H3. So what does that mean? Out of all the hydrogens in the world, the overwhelmingly majority of them are H1, which is the one we talked about here. 1 proton, 1 electron, 0 neutrons. The majority of them are like that. 2% have H2 or H2. What does it mean to be H2 then? How many protons will hydrogen have? Hydrogen is element number 1. I don't care what's going on. Hydrogen is element number 1, so it will always have Z equals 1, which means 1 proton, 1 electron. So then why are we calling it H2? What does the number after the dash always tell you? That's always your mass number, protons plus the neutrons. So then if I have 1 proton, then what must I have for my neutrons now? 1 neutron. The 1 proton plus the 1 neutron is what's getting you the 2 now. So the mass is 2. And then you have H3, 1% of every hydrogen in the world, at 1% of all of them is H3. So here's H3 now. If I'm hydrogen, once again, my Z is 1, so I only have 1 proton. I still only have 1 electron. But now if my mass is 3, how many neutrons must I have? I must have 2 of them now. Because your protons plus your neutrons get you mass number. 1 plus 2 gets you 3. So then how do I get the average atomic mass? Average atomic mass, I will write the formula into the problem for you. But this is the average mass of all the different types of isotopes you have. It is percent abundance of your first isotope times its mass number of that first isotope, plus if you have a second isotope, then you will do percent abundance of that second isotope times the mass number of that second isotope. If you have a third isotope, you repeat the process. If you have a fourth one, repeat the process, so on and so forth. So for hydrogen, if I'm telling you to do this for the 3 hydrogens we have, you would do the 97% times the mass of H1, which is 1, plus for H2, 2% times the mass of 2, plus 1% times the mass of 3, so on and so forth. The rest is very easy. You can get the rest out of your textbook or your notes that we've done in here. Are there any specific questions right now, though, about something you think that might stop you from actually answering that question? Or is there something that you think might be a little confusing that will keep you from doing this tomorrow on the exam? No. What do you think might confuse a person if they had to do this type of calculation? Anybody?
They might not have percent.
They might forget to change it from percent to a decimal. When we're putting percentages in the calculator, how do they go in the calculator? Do we write just 97?
No.
How do you put a percent in the calculator? You have to move the decimal to the left. How many times? Twice. So you would have to type in 0.97. And for 2%, how would that be? 0.02. If it was 1%, 0.01. What if I told you something had 0.01%? 0.0001. Make sure you always move percent signs to the left 2 times. I think the rest of that is easy. Again, that's a regular chemistry thing, so it's something that I do expect you guys to be able to get. That takes care of everything you would have to do. I do want to make a note about isotope notation. There are many ways to write an isotope on an exam or whatever. One way we do it is by writing the name of the element like this, hydrogen, dash, and then we put the mass number. So if I'm talking about hydrogen with a mass number of 3, I would write hydrogen dash 3. If I don't want to write the actual name, you may see us do this, H dash 3. As if it's not confusing already, then we can come over here and write the symbol, and then we can use some superscripts and subscripts. Up here, you would see the mass number. So I would put that mass number there, and then you may see us put the atomic number below like that. Or you may see us write it like this, H, with just the mass number. These are 4 ways to write an isotope. You are expected to be able to know all 4 different ways, so that no matter which way I write it on the exam, you know what information you can get from it. What's the most important thing that's included in all 4 types? The mass number. Why am I not writing the atomic number? The atomic number does not change for hydrogen. Where can you get your atomic numbers? So we don't write stuff that's redundant. If we know that H is number 1, there's no need to write a 1 on all of these because you know the name of the element. So you get your atomic number from here. It's element number 1. It's the mass number that's different because of isotopes. Okay? So that's why you will always see whatever the mass number is, you will see that included in all 4 types. So that takes care of B. Now we get to the meat, C. And that's going to be the bulk of the exam, and that's where most of your money will be. Calculating everything that has to do with the electromagnetic spectrum and energy in waves. Let's get it on. Alright, so now I'm going to the review questions that I asked you guys to do in Chapter 7. Be sure if you want to take a break, get up and go at any time, okay? We're going to keep pushing through this, but if you want to go get some water or whatever, you take care of yourself the way you need to. Alright, well, before we tackle that, let's run through the main points I want you to know. First, electromagnetic radiation. We're talking about waves. Objects that move in a pattern like this. Okay? I'm going to cut a line through the center. Oh, that is not the center. Let's try that again. Not the scale. Alright. Alright, so here's an example of a wave. Just looking at this, if I want to identify where one wave is in the picture that I've drawn, you want to find a point and then see where it repeats. If you don't like trying to figure it out, just find the crest and then see where the crest repeats, which is right here. So here's one wave. Right there. That I've highlighted. There is one wave. That is one wave. So if you ever had to count the number of waves or whatever, you would have to count how many times you see it repeating. If you got like a half part cut off, like kind of like I have right here, then I would just count that as half. One half. Okay? That's one half of a wave. Okay, for your interpretations. Alright, going from one point on the wave to where you see that point repeat, what is this called? The distance from one part of the wave to where it repeats, what do we call that? That's called wavelength. And we use the Greek symbol lambda to represent that. That's called wavelength. So all this time that we've been talking about wavelength, we're literally talking about how long that wave is. Waves that are very large, like radio waves, are as big as buildings, so we could use meters to measure how big a radio wave is. But then you have some waves that are extremely small, like gamma radiation or microwaves and other types of waves. So we use nanometers quite often for that. Okay? Frequency, which has the symbol nu. What is frequency when we say something about something being frequent? What is frequency?
Like often.
It's telling you how often waves are passing by. Specifically, huh? Frequency is the number of waves passing a point in 1 second. How many waves pass by in 1 second? So in physics, you guys will be using some type of electronic devices where you'll probably look at the end of it and then you'll just count how many of those little humps pass by in 1 second as best as you can. So I would see that I count, okay, 3 waves passed by within 1 second. Okay, 3 divided by 1 is 3. And waves is not a unit, that's just how many things we counted. But seconds is a unit. Since seconds is on the bottom, that means the frequency, the number of waves I counted, was 3 waves every second. So we write that unit as 1/seconds, because that's what I have here, is seconds on the bottom. If you don't like having things on the bottom of the fraction, this is why we write it like this, inverse seconds. But the man named Hertz, who studied this, said, screw this negative exponent stuff, I'm going to make up my own unit. I'm just going to call this the hertz. So this is where hertz comes from. So make sure that you are familiar that if you see any one of these three things, they're all frequency, because they're telling you how often waves are passing by each second. Well, I'm not going to have you calculate frequency by counting waves or anything like that, because that's for physics. Instead, what we need to focus on is the relationship between frequency and wavelength. That relationship is defined by this formula. C equals lambda times nu. What is C? That's the speed of light, which is a constant that always remains the same. What is that constant? It is 3.00 times 10 to the 8th power meters per second. That means light waves, you can get I believe that's 300 million or 30 million, 300 million, I think. 300 million of those will go by that many meters. I'm sorry, one wave can pass by 300 million meters in 1 second. That's what that means. Meters per second. That's how far they travel every second. That's for speed of light, which is c. And then your lambda, of course, is wavelength. And what unit must we have that wavelength in to do these calculations? Can we use nanometers for this, for wavelength? If you have meters over here, wavelength needs to be in meters. And then times frequency, which is inverse seconds. And that's how you get m times 1 over s. That's how you get meters per second, just FYI. So make sure that you know how to rearrange this equation. If I want to solve for wavelength, what will the equation look like if I need wavelength? If I need wavelength, wavelength will be equal to what? C over nu. If I needed nu, what would the equation look like? C over lambda. Okay, there's that. We have another equation that we use when talking about waves. That's also why I'm recording. In case I'm going too fast, it will be on YouTube by the end of the day today, and you can just go on there and watch it as many times as you need. We have another equation we use if we want to know how much energy these waves are carrying or equal to. Energy is equal to Planck's constant times frequency. H is called Planck's constant. That's a number just like the speed of light. That number is 6.626 times 10 to the negative 34th power joule seconds. And then, of course, nu once again stands for frequency. It's the same frequency we have here. So if I have E equals H times nu, and then I have this other equation C equals lambda nu, I can actually combine these two equations to make life easier, as we did on yesterday. If I take the C equation, I can rearrange it. Maybe I'll rearrange it for nu. Nu equals C divided by lambda. How about we take that and plug that into here for nu? So that way you get this equation that's just it's just a combination of those two. E equals H times nu. Nu is C over lambda, so H times C over lambda, which you can rewrite it as this, HC over lambda. Energy equals this. So if a problem gives you wavelength, don't waste your time taking the wavelength, plugging it in here to get the frequency, and then take your frequency and plug it into here to get your energy. How about you just take your wavelength and plug it directly into this and get your energy in one step? Do Planck's constant times speed of light and then divide by wavelength. Makes life easier. Once again, wavelength needs to be in meters though, just FYI. 1 meter, nope, let me not confuse you. 1 nanometer is 1 times 10 to the minus 9th meters. So that's how you do your energy calculations when we're talking about waves. That takes care of the first part. If we're talking about a photon, a photon can have other properties besides wavelength and frequency, depending on how it's moving. A photon, which is kind of like a particle of light, that means this is something that can have mass, something that can have a velocity as well. But we're actually not going to include any questions on the exam that mentions velocity. So if you recall us talking about this for a split second, don't even worry about that equation. It's not on there. Let's talk about mass, though. What possible equation could I tie if I'm talking about something behaving kind of like light, but it has mass now? What equation would involve anything from up here? We have this one. It's funny how people never thought that you learn about this equation when you're in like elementary school or middle school, but you never thought you would actually do anything with it. Yes, here we are. Energy of a photon. If you know the energy of a photon, and you can get your energy many different ways by doing this way or this way here, doesn't matter how you get that. But now I could have you plug in that energy or plug in mass. What is C standing for here? That is the speed of light once again. Remember that is squared. Okay? These are how you will have to logically tie one thing to another. These are all the same freaking things. Okay? So I don't care how you get energy. Get the energy of something by using Einstein's equation. Or get your energy from using E equals H nu. Or get your energy by using the combined equation, E equals hc over lambda. Or get your energy from that's the combination. You can use this one as well, but I say just let's be lazy and just use this one, okay? I don't care how you get it. When you get a problem, look and see what's given to you in the problem, and then find out what you're looking for, and then find your way to get the answer. There's many different ways to do this stuff. Now you have another equation as well. If we're talking about electrons, which is where we're talking about, I think that's part B is easy. I'm not going to waste your time on B. C and D, the last two parts. All right, so here is hydrogen, and again, the exam will only talk about hydrogen. Here's the nucleus, and here we go. I messed that up. What do we call this first energy level if you want to use quantum numbers? This is N equals 1. And what is the second one called? N equals 2. And this one here? N equals 3, so on and so forth. So let's talk about an electron. Let's say we have an electron on that first ring, that first energy level. You will be given a question that's going to ask you how much energy must an electron have to live? How much rent should you be paying to live on that first ring? What's your rent? Okay? Think of energy as money. To calculate how much energy you need to live there, here is your equation. Negative 2.178 times 10 to the negative 18th power joules of energy, multiplied by whatever your Z is squared, divided by whatever ring you're trying to live on squared. There is your equation. You want to know how much rent you got to pay to live there? Here it is. That's how you figure it out. What does Z stand for in that equation? It's the same Z as earlier, right? Z is atomic number. And if we're talking about hydrogen, what's the atomic number of hydrogen? 1. Thank God we're only talking about hydrogen. So that means the Z is going to be 1 for these problems here, okay? Now, what does N stand for once again? It's called the quantum number, or principal quantum number, as electron configuration will teach you. That's letting you know which ring you are on, which energy level you are on. So if I am an electron living on the first ring, that's N equals 1, how much energy do I need to live there? We just plug in everything. E equals negative 2.178 times 10 to the negative 18th joules. If I'm hydrogen, my Z is 1, so 1 squared over, if I'm on the first ring, then my N is also 1, so that's 1 squared on the bottom, and we know all of this, 1 squared over 1 squared is 1, and any number times 1 is just that number, so E of the first ring is this number here, 2.178 times 10 to the negative 18th joules. Rings.
N equals 2, N equals 3. What are we changing in the equation then? We're just changing the quantum number. If I ask you about N equals 2, then instead of a 1 down here, you put a 2 in there, 2 squared. If I'm asking you about N equals 3, you put a 3 in there, 3 squared. As we've already done. Now, what if we want to talk about transitioning? For instance, what if we say, I want to move on up from N equals 1 to N equals 3. We would use the delta E equation to talk about the difference, but let's just talk about this qualitatively, meaning let's not talk about calculations. Let's describe what's going on. If an electron is transitioning, if an electron transitions from N equals 1 to N equals 3, what is happening? First, how can an electron do that? What must the electron be able to do? It must absorb energy somehow. You guys did a lab. How did you give those elements and those electrons energy in that lab? We gave it heat. From the problems that we've been reading about and discussing, what's another way to give an electron energy besides just putting it in fire? What can we possibly shine on it? Some type of light, and that's where solar energy comes from. Solar panels, that's how they work. You can add heat, you can shine light, or give it some type of radiation. These are all 3 different ways of doing the same thing. All 3 ways involve you sending some type of energy to the electron so that it can go from N equals 1 to wherever you want to send it, okay? All 3 ways, that is beyond where I can retrieve it. All 3 ways mean the same thing, okay? Shine light, that's the same thing, that's how solar panels work, just FYI. No, you don't have to get that. All I gotta do is do this. And there you go. Think smart, not hard.
I mean, it was on my edge over here.
Yeah, well, I didn't want him to have to get up to do that.
I got it anyway.
I know you did, and I feel bad about that. Okay, so that's qualitatively. Now, and that's how you do what's called exciting. the electron. And then some of you guys on the flame test lab, you kept saying, how did we see light? Because you were exciting the electron. And I kept telling you that's not correct. Because just giving an electron energy is not what causes the atom to give off light. Exciting the electron means it is absorbing the light. It's sucking in the light. So you can't give off light if you are sucking in the light. Exciting means you are sucking in the energy, sucking in the light. Now, what happens though when the electron goes from that higher energy level back down to some level, either the one right below it or the ground state? Then the electron itself will have to give off that energy in order to go back, okay? This is absorbing. Going back to where you came from here is releasing. It took energy or light to make it go to a higher place. So common sense would say if I'm going backwards, I will release that light. And depending on where you're going, that's how you see those different colors. Okay? That's the qualitative discussion of that. Now, quantitatively, now we're talking about calculating some stuff. Okay? So, to calculate this, once again, Juve, what was that equation? You mentioned it earlier. The delta E equation. Basically, what is delta E saying here? It's the change in energy. So it's going to be E final. So where are you going minus E initial, which is where you're coming from. Where you're moving to, where are you coming from? That's what delta E. Any equation that mentions delta means final minus initial. Okay? So example would be, if you have the electron transitioning from n equals 1 to n equals 3, how much energy must be absorbed if it's going from 1 to 3? 1 to 3, how much energy must it suck in? If I'm going from 1 to 3, that means my final position is n equals 3, and I'm starting at n equals 1. So then your E from 3 to 1 would be the energy to be on the third ring minus the energy to be on the first ring. So you would calculate your E, as you did on this equation, for the first ring and the third ring, and subtract them like this, and you'll get your delta E. If you calculate delta E and it's positive, what does that mean if my change in energy is positive? You gained some money. You gained some energy. If my delta E is negative, what does that mean I had to do? If I have that means I lost energy. And we should know when that happens. If I'm gaining energy and I'm looking at the pictures, which of these mean gaining energy? Let's say this is A and this is answer choice B. Which one is gaining energy, A or B? A is gaining energy. I'm absorbing it. I'm Dragon Ball Z Goku. Alright? And then when am I losing energy, having a negative delta E? B, I'm releasing it. Kamehameha! I've just shot all the energy out. There you go. It don't get no better. There's no better analogy, no better metaphor than that. If you never watched Dragon Ball Z, watch an episode tonight. Oh, that's what she mean by no. Well, that's fine. But if you don't understand what the hell's going on, watch Dragon Ball Z. It'll help you understand that. Goku is the electron, and the key energy he sucks up is the energy here, and the Kamehameha is the photon of light that he will release once he sucks in all the energy. No better perfect analogy than Dragon Ball Z. All right? Change in energy. There you go. And that's pretty much it. That's it. That's the exam. Do you have any questions or comments or concerns for the remaining 7 minutes of class we have left? Questions, comments, or concerns? Anything from the review questions in the back of the textbook from chapter 7 that anybody wanted to review or anything like that? No, because I want it to be included in the video. If anybody has any questions. No questions whatsoever? How are we feeling?